Tonight, we're going to look at what may be one of the most striking conformations the James Webb Space Telescope has produced in its mission. Not of cosmic structure, not of the Big Bang model, not of dark energy, of something stranger. The black holes that JWST is finding in the early universe are doing things that Stephen Hawking, in his original framework for black hole physics, said should be effectively impossible. The early supermassive black holes are growing faster than the theory allows. They are appearing in galaxies that should not have been able to feed them. They are sitting at masses that the standard accretion physics cannot explain, and they are forcing a reconsideration of how black holes actually work in the universe. Stephen Hawking, in his groundbreaking work of the 1970s, developed the modern theoretical framework for black hole physics. He showed that black holes radiate energy through quantum effects at their event horizons, the so-called Hawking radiation. He showed that this radiation has specific properties that depend on the black hole's mass. He showed that black holes have a temperature, an entropy, and other thermodynamic properties. The framework Hawking developed has dominated theoretical black hole physics for 50 years. But Hawking's framework, when applied to the growth of the first supermassive black holes in the early universe, predicts specific maximum growth rates that the JWST observations are exceeding. The objects exist. The masses are real. The growth must have happened in the available cosmic time. The exact mechanism is, by every honest description, still being worked out. By the end of tonight, you're going to understand Stephen Hawking's foundational work on black hole physics, the specific predictions his framework makes for how black holes can grow. The JWST observations of early supermassive black holes that are pushing against these predictions, the proposed explanations including direct collapse and super-Eddington accretion, the broader implications for our understanding of black hole physics, the information paradox that Hawking himself wrestled with for decades, and what the JWST observations are telling us about black hole behavior in the early universe. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with Stephen Hawking's foundational work on black hole physics. Hawking was, by any measure, one of the most influential theoretical physicists of the 20th century. He was born on January 8, 1942, in Oxford, England, exactly 300 years after the death of Galileo Galilei. He studied physics at University College, Oxford, graduating with first-class honours in 1962. He moved to the University of Cambridge for graduate work in cosmology, where he was diagnosed at age 21 with amyotrophic lateral sclerosis, a degenerative neurological disease that was expected to kill him within 2 years. He continued his work for the next 55 years, dying on March 14, 2018, at the age of 76. The disease progressively limited his physical abilities, but never his mind. He produced foundational work on cosmology and black hole physics over more than 5 decades. Hawking's most famous result is the discovery, in 1974, that black holes are not truly black. They emit radiation through a quantum mechanical process at their event horizons. This radiation, now called Hawking radiation, carries energy away from the black hole. Over enormously long timescales, the radiation causes the black hole to lose mass, eventually evaporating completely. The discovery was, by every careful description, one of the most surprising theoretical results in physics. Before Hawking's work, black holes were thought to be eternal. After Hawking's work, they were understood to have finite lifetimes. The result was published in the journal Nature in 1974 in a paper titled Black Hole Explosions, followed by a longer technical paper in Communications in Mathematical Physics in 1975. The Hawking radiation framework has several specific properties. The temperature of the radiation depends inversely on the black hole's mass. Smaller black holes are hotter and evaporate faster. Larger black holes are cooler and evaporate more slowly. A supermassive black hole with millions of solar masses has a Hawking temperature of only a billionth of a Kelvin, far below the temperature of the cosmic microwave background. Such a black hole in the current cosmic environment actually absorbs more energy from the cosmic microwave background than it emits through Hawking radiation. The evaporation only becomes significant in the very distant cosmic future when the cosmic microwave background has cooled below the Hawking temperature. The Hawking radiation has specific energy spectrum properties. The radiation is approximately thermal, meaning it has the spectrum of a blackbody at the Hawking temperature. The distribution of emitted particles includes photons, neutrinos, gravitons, and various other species depending on the temperature. The total power emitted depends on the mass and the temperature in a specific way that Hawking calculated precisely. The framework also includes black hole thermodynamics. Hawking showed that black holes have a specific entropy that depends on their event horizon area. The entropy is given by the Bekenstein-Hawking formula, which says that the entropy is 1/4 of the event horizon area in units of the Planck area. The formula combines work by Hawking with earlier work by Jacob Bekenstein at Princeton University, who had proposed in 1972 that black holes should have entropy proportional to their horizon area. The combination of Bekenstein's proposal with Hawking's calculations gave the modern theory of black hole entropy. The Bekenstein-Hawking entropy is, by every careful estimate, enormous for supermassive black holes, far larger than the entropy of all the visible matter in a typical galaxy. Black holes are, in this sense, the most thermodynamically extreme objects in the universe. The black hole temperature and entropy are real physical quantities. Black holes obey the laws of thermodynamics in specific ways. They have temperatures, they have entropies, they have energies. The first law of black hole mechanics, analogous to the first law of thermodynamics, relates changes in black hole properties through specific equations. The second law, analogous to the second law of thermodynamics, requires that total black hole entropy can only increase or stay the same in any physical process. Hawking developed the basic laws of black hole mechanics in collaboration with James Bardeen at the University of Washington and Brandon Carter at the Institut d'Astrophysique de Paris. Their 1973 paper, titled The Four Laws of Black Hole Mechanics, established the formal correspondence between black hole properties and thermodynamics. The correspondence was, by every careful description, one of the most surprising results in modern physics. It established that black holes are not just gravitational singularities but genuine thermodynamic objects with specific quantitative properties. Beyond Hawking radiation, Hawking made numerous other contributions to theoretical physics. He worked with Roger Penrose, then at Birkbeck College in London, to extend the Penrose singularity theorems to the entire universe. The Penrose-Hawking singularity theorems, published in the late 1960s, established that under quite general conditions, general relativity requires the universe to have begun with a singularity. The theorems are foundational to modern cosmology. Hawking proposed, with James Hartle at the University of California, Santa Barbara, the no-boundary proposal for the early universe in 1983, about a counter going up. Engagement tells the algorithm that there is an audience for questions like, will phantom energy shred galaxies, and could a changing dark energy density pull apart atoms? More comments and shares mean the system is more likely to recommend these topics to other curious minds who would otherwise never cross this boundary. One click from you can be the reason someone else discovers that the universe might not fade quietly, but could end in a final, accelerating scream. Pattern interrupt. Pause and imagine that community for a moment. Thousands of people scattered across one tiny planet, watching the same faint supernova light curve on a screen and realizing together what it implies about the fate of everything. Now, let's begin the next step of that shared mission. To understand what James Webb may have just uncovered about dark energy, roll the clock back to the moment no one expects. When astronomers first realized the universe was not just expanding, it was accelerating. In the mid-1990s, the plan is simple. Measure how fast the universe is slowing down. Gravity pulls, expansion coasts. The cosmic movie should be decelerating frame by frame. No one expects the plot twist that is coming. Two rival teams take on the mission. On one side, the Supernova Cosmology Project, led by Saul Perlmutter, building industrial-scale searches with automated telescopes and careful statistics. On the other, the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, moving fast with a global network of observatories and the Hubble Space Telescope. Same goal, different tactics: use exploding stars to weigh the fate of all space. Their tool is a very special kind of stellar catastrophe, type Ia supernovae. When a white dwarf in a binary system steals enough mass from its companion, it crosses a critical threshold and detonates. That threshold is nearly the same everywhere in the cosmos, so the peak brightness of these explosions is nearly standard, a standard candle. If you know how bright the lamp truly is, its apparent brightness on the sky tells you how far away it must be. By the end of tonight, you're going to understand why that simple idea changed cosmology. Measure the light curve of a type Ia supernova, correct for small variations, and you get a remarkably precise distance. Then measure its redshift, how much the lines in its spectrum are stretched toward longer wavelengths. That redshift reveals how much the universe has expanded since the light left the explosion, how far the cosmic fabric has been pulled by the universal wind of expansion. Expectation versus reality comes next. In a universe where gravity from matter rules, distant supernovae should appear slightly brighter than in a universe with constant expansion, because in the past the expansion would have been faster and then slowed down. That deceleration leaves a specific imprint in the brightness-redshift relation. Both teams run the numbers, stack the data, and wait for that decelerating signature. It never shows up. Instead, those high redshift supernovae are dimmer than expected, consistently, uncomfortably. They look farther away than they have any right to be in a slowing universe. The only way to reconcile distance and redshift is to admit something outrageous. Expansion is not breaking. It is speeding up. The cosmic boundary is racing outward faster and faster. To make sense of this, scientists reach back to an old idea almost everyone had written off: Einstein's cosmological constant, L, a uniform energy density of empty space itself. Vacuum with pressure. Put L into the equations of general relativity and empty space pushes, driving galaxies apart the way a constant, invisible wind drives a lightweight spacecraft through the solar system. No one predicts how quickly this resurrected idea will dominate. Within a few years, the LCDM model, lambda cold dark matter, emerges. A universe made of ordinary matter, cold dark matter, and a cosmological constant that fills space. It fits supernova data. It matches the cosmic microwave background. It explains the growth of galaxies and the large-scale structure threaded across billions of light years. For nearly 2 decades, LCDM reigns as the standard model of cosmology. Tonight, we're going to see why that reign is now under pressure, as Hubble refines the local expansion rate, as the Planck spacecraft maps the early universe, and as JWST begins to probe galaxies and supernovae across cosmic time, tiny mismatches appear. Tensions grow. The model that once explained almost everything suddenly has to explain too much, and in those cracks, a new, more dangerous picture of dark energy begins to form. That pressure on the reigning model didn't come from nowhere. It came from a story that seemed, for a while, completely finished. Before we get started with James Webb, go back a century. Einstein writes down general relativity and immediately runs into a problem. His equations say space can't just sit there. With matter and gravity alone, the universe should either expand or contract. To freeze the cosmic picture, he adds a fudge factor, a new term in his equations, the cosmological constant, L, a gentle repulsive pressure filling all of space. For a moment it works. The universe is static, stable, comfortable. Then Hubble points a telescope at distant galaxies and discovers they're all racing away. Space is expanding. The fix was never needed. Einstein reportedly calls L his biggest blunder. The term is abandoned. The mission moves on. Tonight, we're going to watch that blunder come back from the dead. In the late 1990s, 2 teams used type Ia supernovae A as standard candles mapping how fast distant galaxies recede. They expect gravity to slow the expansion. Instead, they find the opposite. The expansion is accelerating. No one expects that result. No one predicts that empty space itself is pushing the cosmos apart. To make sense of it, scientists resurrect Einstein's constant and build a new framework, LCDM. Lambda for the cosmological constant, CDM for cold, dark matter. By the end of tonight, you're going to understand why this model looked unshakable. The cosmic microwave background, mapped by WMAP and Planck, shows tiny temperature ripples that only make sense if the universe is about 70% dark energy, 25% dark matter, and 5% normal atoms. Large-scale galaxy surveys trace a cosmic web whose spacing matches that same recipe. Baryon acoustic oscillations lock in the preferred scale. Supernovae agree. Independent methods, same answer. Mathematically, L is almost offensively simple. It's just an energy density of the vacuum with an equation of state parameter W1 to 1. That single number means its pressure is negative and exactly equal in magnitude to its energy density. It doesn't clump. It doesn't change. It just sits there in every cubic centimetre of space, driving a smooth exponential-like acceleration as the solar system, galaxies and clusters drift farther apart. Cosmologists like this, it's minimal. One extra term in Einstein's equations, no exotic new fields, no rewritten gravity. The spacecraft of theory stays elegant and compact, yet it flies through all the data. The only glaring problem is conceptual. Quantum field theory predicts a vacuum energy vastly larger than what is observed, off by up to 120 orders of magnitude. The most accurate model of the universe contains the worst prediction in physics. So here's the tension. If LCDM fits so much, if the boundary conditions of our universe seemed nailed down, what exactly is JWST seeing that makes some scientists whisper that dark energy might not be constant at all? What if this calm background term is actually a changing, volatile field, one that could, under the right conditions, drive the universe toward a far more violent end than anyone dares to calculate. To test that terrifying possibility, scientists needed more than better equations. They needed a time machine. And in December 2021, strapped to the top of an Ariane 5, that time machine left Earth, the James Webb Space Telescope. Now, let's begin. Imagine a spacecraft with a mirror so large it couldn't fit inside the rocket fairing. Webb's primary mirror spans 6.5 meters, a mosaic of 18 golden hexagons unfolding like a mechanical flower in space. After launch, each segment had to tilt, flex, and align with nanometer precision, turning a pile of folded hardware into the sharpest infrared eye humanity has ever placed beyond the atmosphere. But Webb doesn't just orbit Earth, it was sent 1.5 million kilometers away to the Sun-Earth L2 point, a gravitational balance point trailing our planet. There, a 5-layer sunshield the size of a tennis court blocks heat and light from the Sun, Earth, and Moon. On one side, blazing solar wind and radiation. On the other, a chilling shadow where the telescope can cool to just tens of degrees above absolute zero. That cold, stable darkness is exactly what dark energy experiments crave. The reason is simple. As the universe expands, light from the first galaxies and ancient supernovae is stretched, or redshifted, out of the visible and deep into the infrared. Hubble could glimpse some of this, but much of the early universe slipped beyond its reach. Webb lives in that infrared realm. Its detectors are tuned to wavelengths where the earliest cosmic beacons now shine, letting the mission see galaxies less than a few 100 million years after the Big Bang. Tonight, we're going to follow 3 of Webb's most powerful tools for decoding that expansion. NARCam, the near-infrared camera, takes ultra-deep images, stacking photons from galaxies at redshifts greater than 10, mapping how structure built up over billions of years. NIRSpec, the near-infrared spectrograph, splits that light into spectra, measuring precise redshifts and chemical fingerprints, turning faint smudges into exact distances and velocities. And NIRIS adds slitless spectroscopy and exquisite exoplanet transit measurements, quietly sharpening the cosmic distance ladder that underpins every dark energy calculation. Here's the pattern interrupt. Webb was never billed as a dark energy mission. That role was reserved for Euclid and NASA's upcoming Roman Space Telescope, purpose-built to survey millions of galaxies and supernovae. Webb was sold on first galaxies, star formation, and alien atmospheres. No one expects a general-purpose observatory to challenge the foundations of cosmic acceleration. No one predicts its deep fields might hint that dark energy's behavior changes with time. And absolutely no one anticipates that its exoplanet-calibrated distance scales could tighten the Hubble tension instead of resolving it. By the end of tonight, you're going to understand how a telescope designed to read the universe's childhood diary may also be writing the first draft of its obituary. Because when Webb stares back across 13 billion years, the way those galaxies stretch, cluster, and dim may reveal whether dark energy is calm, restless, or racing toward a future that tears the cosmos apart. To see why Webb's results are so unsettling, you first need to see the picture scientists thought was rock solid. Tonight, we're going to walk through the universe's expansion history the way it was drawn in textbooks for decades before this new mission started pushing beyond that comfort zone. Before we get started, imagine a simple graph in space. Horizontal axis, time since the Big Bang. Vertical axis, the scale factor, a number that tells you how big the whole system is compared to today. Early on, that curve rockets upward almost vertically. That's inflation, a brief, furious growth spurt where the cosmos doubles in size again and again in a tiny fraction of a second. Then the line eases off. After inflation, the universe is dominated by radiation, light, high-energy particles, and a searing plasma wind racing through space. In this radiation-dominated era, expansion keeps going, but the slope is shallower. Gravity from all that energy is pulling back, trying to slow the stretch even as the overall scale keeps increasing. As the universe cools and expands, matter takes over. Ordinary atoms and dark matter outweigh radiation, and the graph bends into an even gentler rise. This is the matter-dominated era. Galaxies and clusters assemble, pulled together by gravity, while the expansion gradually decelerates. Designed for a universe where gravity rules, this middle section is smooth, predictable and tightly constrained by observations of galaxies and the cosmic microwave background. Then something dramatic happens late in the game. Several billion years ago, the curve stops flattening and begins to tilt upward again. The expansion stops slowing and starts accelerating. In the standard picture, this is when dark energy takes over. The graph develops a subtle but unmistakable upward bend, as if some invisible pressure in the fabric of space is pushing every galaxy away from every other galaxy, faster and faster. Cosmologists describe that pressure with a single number, the equation of state parameter, W. It relates dark energy's pressure to its density. If W equals 1, dark energy behaves like a true cosmological constant, a fixed energy of empty space that doesn't dilute or change with time. In LCDM, the flagship model of modern cosmology, W is assumed to be exactly 1 at all times, everywhere. That one assumption locks in a very specific prediction. It dictates how fast structures should grow, how quickly galaxies and clusters should form, and exactly how that expansion curve should arc, from inflation through matter domination into late-time acceleration. No one expects it to be a vague sketch. It's a precise, testable trajectory. Now, let's begin to see the tension. By the end of tonight, you're going to understand why Webb's deep look into the early universe lets scientists lay that theoretical curve over real galaxies and ask a dangerous question. Has dark energy's influence always followed that line, or has the universe been quietly drifting off script? Now, let's begin to see how that dangerous question shows up in the numbers. The universe has a speed limit for expansion, a single parameter that tells you how fast space itself is stretching right now. It's called the Hubble constant, h0, h0. Measured in kilometers per second per megaparsec, it says, for every megaparsec, about 3.26 million light-years, galaxies recede this many kilometers per second just from the expansion of space. This one number sits at the center of modern cosmology. Get h0 right and the entire cosmic timeline, from the first light to the fate of planets and galaxies, falls into place. Get it wrong, and the whole system of equations that describes dark matter, dark energy, and the growth of structure starts to wobble. By the end of tonight, you're going to understand why that wobble now looks less like noise and more like a crack. There are two main ways to measure h0. One looks to the early universe, to the cosmic microwave background, the faint afterglow of the Big Bang. Missions like Planck treated that glow as a fossil record, fitting the ripples in that light with the LCDM model, the standard mission plan for the cosmos with cold, dark matter, and a cosmological constant. The other way looks to the late universe, building a distance ladder step by step, using Cepheid variable stars, red giant branch stars, and type Ia supernovae in real galaxies. In LCDM, those two approaches should land on the same answer. Early time physics sets the initial conditions. Late time measurements read out the result. Expectation? One universe, one H0. Reality? It looks like two universes that don't agree about how fast they're flying apart. Planck's early universe analysis points to about 67 kilometers per second per megaparsec. Late-time distance ladder missions cluster around 73. The error bars have shrunk as instruments improved, but instead of converging, the measurements have pulled apart. The boundary between quirk of data and something is wrong has been crossed. This isn't a rounding error, it's a statistically significant, persistent tension. At first, many scientists hoped for a simple calibration glitch, a misbehaving detector, a dusty galaxy, a miscounted Cepheid. No one expects the entire framework of dark energy and gravity to be on the line. No one predicts that independent teams with different telescopes and methods would keep landing on the same split universe. Tonight, we're going to follow the spacecraft that just stepped into this fight. JWST's sharp infrared vision can isolate Cepheids even in crowded galactic centers, resolve red giant branch stars deep in dust, and track distant supernovae across cosmic time. If there were hidden biases in the distance ladder, Webb should reveal them, smooth the numbers, bring 73 down towards 77. But early Webb campaigns are hinting at something far stranger. The precision is going up. The disagreement is not going away. And in the next section, those clean, sharp JWST images are going to force a choice. Fix the ladder, rewrite dark energy, or admit that the law of gravity itself may need to be broken. So if the ladder might be broken, how does James Webb actually climb it? Tonight, we're going to walk up the universe's measuring stick, rung by rung, and watch how this new spacecraft turns vague guesses into hard numbers. Now, let's begin. At the very bottom of the cosmic distance ladder is something almost disappointingly simple: geometry. For nearby stars, scientists use parallax. As Earth moves around the Sun, a nearby star appears to shift slightly against the background of more distant stars. Measure that tiny angle, know the size of Earth's orbit, and you can calculate the star's distance with pure trigonometry. No exotic physics, just a cosmic triangle. But that only works in our immediate solar neighborhood. Beyond a few thousand light-years, the angles get too small, so the next rung uses special stars called Cepheid variables. Their brightness rises and falls with a regular rhythm, and there is a tight relationship between their pulsation period and their true luminosity. Watch how fast they pulse, compare how bright they look, and their distance drops out. These Cepheids live in nearby galaxies, so they let scientists extend the scale from our local system to other islands of stars. Then comes the third rung, type Ia supernovae. When a white dwarf in a binary system steals enough mass from its companion, it detonates in a nearly standard way, reaching almost the same peak brightness every time. These explosions are so luminous they can be seen across billions of light-years, turning them into beacons that map the expansion of space itself. Here is where James Webb changes the game. Hubble could see Cepheids and red giant branch stars, but it had to peer through clouds of dust that absorb and scatter visible light, introducing subtle, dangerous biases. Webb's mirrors are tuned to infrared. That longer wavelength light slips through dust, that would block optical telescopes so JWST can measure Cepheid flickers and the sharp cutoff of red giant branch stars with far less interference. The result is cleaner distances, fewer systematic errors, and a tighter calibration of every rung above. But distance alone is only half the story. To probe dark energy, Webb also has to measure how fast galaxies are receding. That's where spectroscopy and redshift come in. Instruments like NearSpec spread a galaxy's light into a spectrum, revealing fingerprints of elements: hydrogen, oxygen, nitrogen. In a laboratory, those lines sit at known wavelengths. In a distant galaxy, they are stretched to longer, redder wavelengths by the expansion of space. The amount of that shift tells you how much the universe has expanded since that light left. Pattern interrupt. Not every path to distance uses candles at all. JWST also watches how massive galaxy clusters warp space and bend the light of galaxies behind them, a phenomenon called gravitational lensing. By mapping the distorted arcs and stretched images, scientists can infer the cluster's mass, the geometry of space, and independent distance estimates. That, in turn, tracks how cosmic structure has grown over time. By the end of tonight, you're going to understand that with these tools working together, parallax, Cepheids, red giants, supernovae, redshift, and lensing, Webb can trace the expansion history from the relatively nearby universe all the way out to galaxies shining less than 500 million years after the Big Bang. And in the next section, those measurements will do something no one predicts. They will force cosmology to choose between a restless, dark energy, a broken theory of gravity, or a universe racing toward a far more violent ending than anyone expected. Those possibilities stop being abstract the moment a new spacecraft starts testing them, and that's where James Webb delivers its first real strike. Now, let's begin with the quietest, most dangerous question in modern cosmology. Is the Hubble constant wrong, or is the model of the universe wrong? For a decade, the hope has been simple. Somewhere, hidden in the distance ladder that turns Cepheid stars and supernovae into cosmic yardsticks, there must be a subtle mistake, a calibration glitch, dust in the way. Something that lets the late-time expansion rate drift high while the early universe value from the cosmic microwave background stays low. Before we get started on the drama, it helps to see what Webb actually did. Teams of scientists turned JWST toward the very same galaxies Hubble used to anchor the distance ladder, re-observing their Cepheid variable stars in the infrared. In that wavelength range, dust becomes almost transparent, so the solar neighborhoods around those stars stop acting like dirty windows and start behaving like clean laboratory measurements. The mission wasn't chasing pretty pictures. It was hunting for systematic errors that could drag the Hubble constant back down. Expectation. Hubble's Cepheids are contaminated by dust and crowding, making them look slightly brighter and closer than they are. Reality. When Webb's sharper infrared vision resolves those crowded stellar fields, the distances barely move. The brightness period relation tightens, the scatter shrinks. The ladder holds. This is a pattern interrupt for the entire field. No one expects the newest, most precise eye in space to come in, recheck the foundation of the local distance scale, and then calmly say, the higher late time H0 looks real. Yet that is what the early JWST Cepheid campaigns have discovered. The refined measurements still point to a Hubble constant around 70 plus kilometers per second per megaparsec, while the Planck satellite's early universe reading sits stubbornly near 67. The boundary between annoying discrepancy and new physics is now uncomfortably thin. If the late-time universe is expanding faster than the LCDM model predicts, something in the cosmic energy budget must be changing. Either dark energy is not a perfectly constant cosmological constant, or gravity itself behaves differently on the largest scales than Einstein's equations suggest. Both options push the universe beyond the simple picture that worked so well for 20 years. By the end of tonight, you're going to understand why that matters for the fate of everything, from galaxies to atoms. Because if dark energy is evolving even slightly, the long-term story of the cosmos changes. A gentle heat death gives way to more extreme endings. And absolutely no one anticipates the possibility that Webb's confirmation of a stubbornly high Hubble constant might be the first hint that dark energy is not just there in the background, but slowly getting stronger. If the expansion is already running ahead of schedule, what happens if that trend continues? If the expansion is already running ahead of schedule, you need to know what exactly might be pushing on the accelerator. Before we get started with James Webb's most unsettling clues, you need a clear map of the possibilities. Tonight, we're going to turn dark energy from a vague mystery into a small set of concrete options. The simplest option is the cosmological constant. In plain language, it says empty space is never truly empty. Every cubic meter of space, from your living room to the most remote void beyond the visible galaxies, carries the same tiny, fixed energy. It doesn't clump, it doesn't flow, it doesn't change with time. In the equations, this looks like an equation of state, W=1, meaning the pressure is exactly the negative of the energy density. That negative pressure acts like tension in the fabric of the cosmos, making expansion speed up. If that picture is right, the story is almost boring. The acceleration continues forever, but gently. Galaxies drift apart, stars burn out, the solar system coasts into a thin, cold future. No one expects drama. The universe just fades. But there is a more restless possibility, quintessence. Instead of a rigid cosmological constant, scientists imagine a scalar field filling space like a ghostly fluid with its own potential energy landscape. This field can slowly roll down that landscape as the universe expands, changing how much energy it carries and how hard it pushes. In those models, W is not locked at 1. It can be 0.9, 0.95, maybe drifting with time. By the end of tonight, you're going to understand why a tiny deviation from W1 is a huge deal. It means dark energy is not a fixed property of space, but a living field with a history and, possibly, a fate. Then there is the truly alarming regime, phantom energy. Here, W drops below 1. That single inequality flips the script. Instead of thinning out, the dark energy density increases as space expands. The more room there is, the more repulsive energy you get. Run that forward, and the expansion does not just accelerate, it runs away. Galaxies are torn from one another, then solar systems, then stars, then planets, and finally atoms themselves in a finite-time catastrophe known as the Big Rip. No one predicts that outcome lightly, but mathematically, it is right there. Around these main characters orbit even stranger ideas. K-essence fields whose pressure depends on their motion, dark energy that trades energy with dark matter, and modified gravity where the equations of general relativity are tweaked so that space-time curves differently on the largest scales. In those views, what looks like a new energy component might really be a failure of the old gravitational law. Now, let's begin to see where Webb fits by measuring how fast distant galaxies recede, by timing type Weir supernovae. By watching gravitational lensing sculpt the images of faraway clusters, JWST traces both the expansion history and how cosmic structures grow over billions of years. A true cosmological constant leaves a very specific fingerprint on those curves. A living, evolving dark energy field leaves a different one. If the data keep drifting away from the W-Chow-1 track, the universe we inhabit may be far more volatile than the quiet heat-death picture suggests. And if hints of phantom-like behavior survive every cross-check, the question won't just be how the universe ends, but how soon that countdown has already advanced. If dark energy's fingerprint on the expansion history is already looking unstable, JWST has thrown in a second, even stranger clue. It is not just how fast space stretches. It is what has managed to grow inside that stretching space. Now, let's begin with how you even see galaxies less than 500 million years after the Big Bang. Deep surveys like Sears, JADES, and Glasspoint JWST at tiny patches of sky and refuse to blink. The spacecraft stares for tens of hours, collecting every photon from regions far beyond the outer planets, where the light has been traveling for over 13 billion years. Those smudges are not noise, they are entire systems of stars. In those pencil beam views, scientists measure galaxies at redshifts greater than 10. That means the universe was under 4% of its current age when that light left. According to the standard LCDM picture, with a cosmological constant dark energy and cold dark matter, there should be galaxies there. Small, clumpy, faint ones. Proto-galaxies just learning how to shine. But that is not what JWST discovered. Some of these objects appear too massive, too bright, and too well organized for such an early cosmic morning. Prediction: a few million or tens of millions of solar masses in stars. Observation: candidates weighing in at 1 billion solar masses or more, with surprisingly smooth profiles and heavy element signatures that suggest multiple generations of star formation have already come and gone. No one expects that level of maturity so soon after the Big Bang. This is where dark energy quietly re-enters the story. In a universe with a particular dark energy history, gravity only has so much time and so much effective strength to pull matter together against the overall expansion. The growth of structure follows a calculable curve, tiny ripples in the early plasma, to dark matter halos, to galaxies, to clusters. Change the behavior of dark energy, and that growth curve bends. If galaxies are assembling faster and earlier than LCDM simulations allow, something in that chain is off. Maybe the masses are being overestimated because dusty, compact starbursts mimic huge systems. Maybe star formation was wildly efficient, turning gas into stars with almost no waste. Or maybe the underlying cosmology, the balance between dark matter, dark energy, and gravity itself, needs an upgrade that no one predicts. Tonight, we're going to use these ancient galaxies as a kind of stress test. By the end of tonight, you're going to understand why a few bright smudges at Z-Zone 10 can threaten the quiet, eternal heat death narrative. If early structures grew too quickly, that could mean gravity behaved as if it was stronger in the past, or that dark energy's repulsive influence was weaker. And if dark energy has been slow to rise but is catching up now, could that late acceleration race toward a future where the same force that once allowed galaxies to form begins tearing them apart, piece by piece? If that balance between gravity and dark energy is already shifting, the next question is brutal. Did the universe ever play by the simple rules scientists thought it did? Cosmologists went into the James Webb mission with a clean narrative. In the beginning, the universe is hot, dense, and almost perfectly uniform. Tiny ripples in density, 1 part in 100,000, slowly grow under gravity. Billions of years later, those ripples become galaxies, clusters, and the vast cosmic web. That picture is elegant, predictable. Now, let's begin to see where it cracks. When JWST opened its gold-plated eye on deep space, it was supposed to watch the earliest stages of that long construction project. A few small, clumpy proto-galaxies. A universe still under scaffolding. No one expects to find fully formed skyscrapers in a city that's only just been built. Yet that is almost what the spacecraft discovered. In deep surveys like JADES and SEERS, JWST sees galaxies less than 400 million years after the Big Bang that are bright, compact, and massive, sometimes rivaling the Milky Way's stellar mass compressed into a fraction of its size. It sees protoclusters, knots of galaxies already gathering in the young cosmic web. Designed to reveal a universe in its infancy, JWST keeps finding objects that look suspiciously mature. Here's the pattern interrupt. On the largest scales, the early universe still looks remarkably smooth, as if the cosmic web is only just beginning to emerge. But on smaller scales, individual structures seem to have grown up too fast. Too smooth background, too structured details. That contrast is the clue. In the standard picture, dark matter provides the invisible scaffolding. It collapses first, forming halos whose gravity pulls in normal gas, ignites stars, and builds galaxies. Dark energy, by contrast, acts like a repulsive pressure in the fabric of space, accelerating expansion and stretching the cosmic web. Early on, dark matter wins, gravity dominates and structure grows quickly. Later, as space expands, dark energy takes over and the growth of new structure slows, as if the universe is switching from construction to demolition. By the end of tonight, you're going to understand why JWST is making that schedule look suspicious. If dark energy's influence turned on a little earlier than expected, or evolved differently over time, it would subtly change when and how galaxies and clusters assemble. Structures might form faster in some eras, then freeze out earlier, leaving a universe that looks both prematurely mature and strangely smooth. Some teams are already testing models where dark energy is not a simple constant, but a field that changes strength, or even briefly hands gravity extra leverage before slamming on the brakes. And if that still cannot reconcile what JWST sees, the two early giants, the delicate large-scale pattern, then the next step is even more radical. Before we get started on dark energy's possible futures, some scientists are whispering a deeper heresy. Perhaps it's not just dark energy that needs to change, but gravity itself. What happens to the universe if Einstein's law starts to bend? So instead of diving straight into equations that might bend, pause and watch the whole universe live its life in fast forward. Close your eyes for a second and clear the slate. Now, let's begin. At first, there is no space full of galaxies, no planets, no solar system, just a hot, blinding plasma, so dense that light cannot travel freely. The scale factor is nearly zero. Distances are tiny, but energy is enormous. Quantum jitters in that early field, minuscule fluctuations in density, flicker everywhere. Then expansion hits the gas pedal. Space itself stretches, and those tiny quantum ripples get dragged outward, inflated to cosmic size. As the universe expands, it cools. Protons and electrons finally slow down enough to combine into the first atoms. Hydrogen, helium. A transparent universe is born. Light, once trapped, can now fly. This is the afterglow scientists call the cosmic microwave background, the frozen snapshot of that moment when the scale factor has grown enough for space to become clear. But that clarity comes with darkness. No stars yet, no galaxies, just a thin, neutral fog. These are the cosmic dark ages. The only structure is invisible, those stretched-out quantum seeds, slightly denser regions where gravity has a tiny head start. Over hundreds of millions of years in our mental time lapse, those seeds begin to grow. Gravity pulls more matter into the overdense spots. Filaments form, voids empty. A vast cosmic web starts sketching itself across expanding space. Then, a pattern interrupt. Suddenly, pinpricks of light. The first stars ignite, pouring ultraviolet radiation into the fog. They carve out bubbles, reionizing the gas. Small galaxies assemble along the filaments, then merge into larger systems. By the end of tonight, you're going to understand that every graceful spiral and every giant elliptical began as those quantum wrinkles, amplified by relentless gravitational attraction. During this era, matter rules. The expansion is still slowing because gravity from all that matter is pulling back on the cosmic fabric. The scale factor grows, but more grudgingly. Structure formation is efficient, clusters and superclusters lock into the web. Dark energy is present, but its influence is almost negligible, a quiet background term in Einstein's equations. Then the balance shifts. As expansion thins out matter, its gravitational pull weakens. Dark energy does not dilute the same way. At some critical time, the universe crosses a boundary, from matter-dominated to dark energy-dominated. Now the expansion begins to accelerate. Galaxies that once coalesced are carried apart faster and faster. The same force that allowed structures to form now competes with a new driver that wants to pull everything beyond everything else. Run the time lapse forward, and the cosmic web stretches. Filaments lengthen, voids balloon. In some dark energy models, the acceleration stays gentle. In others, it grows so violently that it could one day tear clusters, galaxies, even atoms apart. No one expects a calm, eternal universe anymore. No one predicts a simple, forever slowing cosmos. Absolutely no one anticipates how strange the endgame might be if dark energy keeps changing. Now zoom back along the timeline, not to the beginning, but to those first billion years when stars are just turning on and galaxies are still raw and compact. That is the window the James Webb Space Telescope opens. Tonight, we're going to use this spacecraft as a time machine, catching galaxies in the act of forming along those primordial filaments. For the first time, scientists are not just theorizing about that transition from darkness to light. They are watching it frame by frame and using it to test whether the universe's acceleration and its possible fate matches the story this grand time-lapse tells. Those newborn galaxies give one timeline of the universe's growth, but to test dark energy itself, scientists need a different kind of clock, a cosmic explosion so reliable that it can turn the entire sky into a ruler. That's where a very special kind of stellar death comes in. Before we get started, rewind to the 1990s. Two rival teams used Type Ia supernovae, white dwarfs pushed over a critical mass, to measure distances across space. These explosions reached nearly the same peak brightness, so if you know how bright they are in reality and how faint they look, you can work out how far away they must be. Plot that distance against redshift and you get the expansion history of the cosmos. That is how acceleration was discovered in the first place. The catch is reach. Hubble could track these supernovae out to redshifts of about 1.5 before the light slipped into the infrared and the host galaxies became too faint, too dust-obscured, too far beyond the solar system's old tools. JWST changes that overnight. Its infrared eyes can see Type Ia supernovae in galaxies so distant that their light has been stretched for more than 10 billion years. Now, let's begin. Dedicated JWST campaigns piggyback on wide surveys that flag new supernovae, then swing the spacecraft back to watch them rise and fade. Programs tied to fields like Sears and Jades are catching explosions in galaxies that existed when the universe was less than a quarter of its current age. JWST measures their light curves, tracks how quickly they brighten and dim, and takes spectra that slice the light into colors, even through heavy dust that would blind optical telescopes. Each supernova becomes a point on a grand diagram. Brightness versus redshift, distance versus time. String enough of those points together across many epochs, and you reconstruct how the expansion rate has changed. If dark energy is a simple cosmological constant, the equation of state parameter W should stay pinned at 1. The curve should follow one precise track. Any deviation, any bend in the wrong direction, hints that W might evolve. Tonight, we're going to focus on that tiny bend. Early JWST supernova data within current uncertainties still support an accelerating universe. The overall story matches what Hubble and ground-based observatories discovered, but when cosmologists fit the best models, some solutions allow W to drift slightly over time, nudging above or below 1 at different redshifts. Not enough to claim a revolution, just enough to keep theorists awake. And here is where the stakes jump. By the end of tonight, you're going to understand why even a small shift in W matters. If future JWST samples with hundreds of well-measured Type Ia explosions show W dipping below 1 or clearly sliding with redshift, no one expects that to be a statistical fluke. No one predicts the cosmological constant to suddenly misbehave. Absolutely no one anticipates what that would mean for the far future. A dark energy that grows, a repulsive wind that strengthens, and a universe where the expansion does not merely continue, it tears cosmic structures apart. The next step is to ask, what kind of dark energy could do that? If dark energy can grow, there has to be a way to see its fingerprints, not just in how space stretches, but in how cosmic structures fight back. Gravity pulls matter together. Dark energy pushes the fabric of the universe apart. Where those two forces collide, something remarkable happens. Light itself bends. This is gravitational lensing, one of Einstein's strangest and most powerful predictions. Put a massive galaxy cluster in the path between you and a more distant galaxy, and the cluster warps space-time around it. Light from the background galaxy does not travel in a straight line. It follows the curved geometry, wrapping around the cluster, producing stretched arcs, duplicated images, and sometimes eerie rings that look like the universe has drawn a circle around a hidden boundary. Now, let's begin. Tonight, we're going to watch James Webb turn those distortions into a cosmic diagnostic tool. With its sharp infrared vision, JWST can stare at lensing clusters like Abell 2744 or SMACS 0723 and resolve galaxies that existed when the universe was only a few 100 million years old. Those galaxies are faint, redshifted, and buried in glare. Older telescopes saw hints. JWST sees full shapes, twisted arcs, tiny knots, mirrored copies. Every one of those warped images encodes two things at once: how much invisible mass is in the lensing cluster, and how the overall geometry of the universe stretches the light's path. By carefully mapping where the arcs appear, how strongly they are magnified, and how their redshifts compare, scientists reconstruct detailed mass maps of the clusters and measure how structure is distributed across space. Here is the crucial link to dark energy. The amount of lensing and the sheer number of massive clusters at different cosmic times depend on how fast structures have grown. If gravity has had billions of years to pull matter together, galaxy clusters become heavier and more common, and they bend light more strongly. If dark energy has been pushing back harder, accelerating the expansion and thinning out the cosmic web, structure growth slows, clusters are rarer or less massive, and lensing signals weaken. By the end of tonight, you're going to understand why combining these lensing maps with other surveys turns JWST into a referee between competing universes. One universe is LCDM, the standard model where dark energy is a simple cosmological constant, and gravity follows Einstein's rules. The other universes allow dark energy to evolve or even tweak gravity itself. When JWST's lensing data are stacked with supernova distances, galaxy redshift surveys, and cosmic microwave background measurements, scientists can ask a sharp question. Does the observed growth of structure match the expansion history? Or is something being suppressed or strangely enhanced beyond expectations? If the growth inferred from lensing refuses to line up with the expansion rate inferred from standard candles and the Hubble constant, no one expects that to be a trivial calibration error. No one predicts that a simple tweak will patch both. Absolutely no one anticipates what it would mean if both sides stay stubborn, because then the conclusion is inescapable. Either dark energy is changing with time, or the law of gravity on cosmic scales is not the law written in our textbooks. And JWST is quietly pushing the data toward a point where the universe will have to choose. The next clue comes from an even more unsettling place: how fast the earliest galaxies appeared, and what that says about just how strong gravity and dark energy really are. Those early galaxies are already bending the rules, but to really corner dark energy, scientists need something even cleaner than galaxies or exploding stars. They need a way to measure the expansion of space itself without climbing the entire cosmic distance ladder first. That's where an idea with a surprisingly poetic name enters: standard sirens. If standard candles are the universe's lighthouses, then standard sirens are its alarms. These are gravitational wave events, cataclysmic mergers of neutron stars or black holes, where the ripples in space-time carry, encoded in their shape and strength, the true luminosity distance to the source, no calibration to nearby planets, no reliance on the solar system's parallax measurements, no stacking of rungs on a fragile ladder. The trick is subtle but powerful. As two neutron stars spiral together, the gravitational wave signal chirps. Its frequency and amplitude ramp up in a way that depends only on the masses, the orbital geometry, and how far the system is from us. From that waveform, the distance drops out of Einstein's equations directly. Tonight, we're going to treat space-time itself as the measuring stick, but distance alone is not enough. To track the expansion, scientists also need redshift, the amount the universe has stretched the light on its journey to us. That requires an electromagnetic counterpart, a kilonova flash, a fading afterglow, a host galaxy, whose spectrum reveals how much the universe has expanded. when the first neutron-star merger, GW170817, lit up the sky in 2017, telescopes across the planet and in space swung toward a single galaxy, combining gravitational waves and light to give both distance and redshift in one shot. Now, let's begin to see where JWST changes the game. Ground-based telescopes can chase these mergers nearby, but at higher redshifts the light shifts into the infrared and fades into the glow of the distant universe. JWST was built for that regime. Its infrared eyes can pick out the faint, dust-obscured afterglows of mergers billions of light-years away, where the cosmic expansion is more strongly influenced by dark energy. By the end of tonight, you're going to understand why that matters. With JWST, scientists can resolve the host galaxy, measure its redshift with exquisite precision, and untangle the galaxy's star, formation history and chemical fingerprints. That reduces the uncertainty in each standard siren measurement. One merger is a curiosity. Hundreds, scattered across cosmic time, become a map of how the expansion rate has changed. Pattern interrupt. Up to now, dark energy tests have leaned heavily on supernovae and galaxies, but standard sirens do not care how bright a star should be or how galaxies evolve. They listen to the pure stretching of space-time, providing an independent handle on the Hubble constant and the expansion history. This field is still young. No one expects the early catalogues to settle the dark energy argument overnight. No one predicts a single golden event that suddenly reveals the fate of the universe. But as JWST's deep galaxy surveys fill in the background and future gravitational wave missions detect mergers at ever greater distances, a multi-messenger network begins to form. Before we get started on the most extreme dark energy models, remember this. JWST is one spacecraft in a growing system of cosmic witnesses. Together, gravitational waves, supernovae, galaxies, and the infrared eye of JWST, they may finally tell us whether dark energy is truly constant or quietly evolving toward a future where the expansion does more than stretch space. It might, in the most ominous scenarios, tear the universe apart, from the largest clusters down to the atoms themselves. If those cosmic witnesses tell us how fast space is stretching, the next question is where that stretching leaves its fingerprints. Not just in lonely supernovae or distorted galaxies, but across the entire scaffolding of the universe. Tonight, we're going to follow dark energy's trail into the largest structure ever mapped, the cosmic web. On the biggest scales, galaxies are not sprinkled randomly through space. They line up along titanic filaments, pile into vast walls, and leave enormous voids in between. Galaxy redshift surveys turn this pattern into a three-dimensional map. Measure each galaxy's redshift to get its distance, plot millions of them, and a hidden architecture appears, a foamy network whose growth history records a billion-year tug-of-war between gravity pulling matter together and dark energy pushing space apart. Traditional surveys like SDSS and DESI sweep huge regions of the sky, but they mostly see the nearby universe. JWST does something different. It drills narrow, incredibly deep cores through that web. In fields like JADES and SEERS, it picks up galaxies when the universe was only a few % of its current age, turning tiny patches of sky into time tunnels that reach back more than 13 billion years. From those slender slices, scientists can measure how strongly galaxies cluster at very high redshift. Do they clump into tight knots? Do filaments already look mature, or are they just beginning to emerge from a smoother sea of matter? By the end of tonight, you're going to understand why that pattern matters so much for dark energy. In a universe with a simple, constant W dark energy, Einstein's cosmological constant, there is a precise prediction for how fast structure should grow with time. Gravity amplifies tiny ripples into galaxies and clusters, while dark energy gradually chokes that growth as expansion accelerates. Compare clustering strength at different redshifts, and the theory says exactly how the contrast between dense filaments and empty voids should evolve. JWST's high redshift slices let scientists run that comparison across an enormous span of cosmic time. Early hints, combined with other surveys and weak lensing maps, point to an intriguing pattern. The amplitude of matter clustering, often captured by a parameter called sigma 8, seems slightly lower than the standard lambda CDM model predicts. Not wildly off, just enough to be annoying, just enough to be persistent. No one expects a universe this well-modeled to keep slipping out of the equations in the same direction. A higher Hubble constant here, galaxies forming too early there, and now a Webb that is a bit less clumpy than forecast. No one predicts that 3 independent clues would all whisper the same thing, and absolutely no one anticipates what it might mean if the entire dark sector is hiding new physics. Because if the Webb's growth is off, dark energy may not be a quiet, constant background at all. It may evolve, interact, or even switch behavior in ways that change not only how the universe expands, but how it will ultimately end. If the cosmic Webb's growth is off, the next question is brutal in its simplicity. Is dark energy itself changing with time? Tonight, we're going to step right into the equation that lets scientists ask that, and see why James Webb's data makes the answer more unsettling than it used to be. Before we get started, take the usual expectation. Dark energy is a cosmological constant, one number, forever, W1. No evolution, no drama. Reality? Cosmologists now reach for a more flexible tool, an evolving equation of state, written as WZ sun W0 plus weights 1, A, where A is the cosmic scale factor. One parameter, W0, sets dark energy's pressure today. The other, WA, controls how that pressure changes as the universe expands. In plain language, this lets the mission fit 2 things at once: how strong dark energy is right now, and how fast it might be drifting over cosmic time. Designed for a silent, constant background, it suddenly behaves like a dial with both a value and a slope. And when that dial is connected to the fate of the entire solar system, tiny changes matter. By the end of tonight, you're going to understand why combining James Webb with every other probe in cosmology has become so important. On its own, JWST measures distances and redshifts to galaxies and supernovae deep into the early universe, mapping how space has stretched from redshift Z1 to today. But when those measurements are folded together with the cosmic microwave background, baryon acoustic oscillations, and older supernova surveys, scientists can carve out allowed regions in the JWA plane. If dark energy were a perfect cosmological constant, the point W0, SWAN WA0, would sit squarely in the middle of the data. Instead, current best fits often slide a little off-center. Some combined analyses that include Webb's early galaxy and lensing constraints still find results statistically consistent with W1, but the peak of the probability sometimes leans toward W0 a bit below 1 and WA slightly negative. No one expects that small numerical nudge to mean much at first glance, but its implication is dramatic. AW dipping below, one at certain redshifts, hints at phantom behavior, where dark energy's density grows as the universe expands, rather than thinning out. In those models, the expansion does not just accelerate, it runs away. Here is the catch. Systematics in supernova brightness, uncertainties in galaxy evolution, calibration differences between instruments, and the exact model assumed for the dark sector all leave plenty of room for error. With limited JWST samples so far, absolutely no one anticipates a courtroom-level verdict on evolving dark energy. The door is simply more open than it was before Webb started watching. But if future data push harder into W1 and WA trending downward, the story changes. Then the universe's long-term forecast shifts from a slow, cold fade into a heat death to something far more violent, a finite-time big rip where galaxies, stars, planets, and finally atoms are torn apart by expansion itself. And in the next section, the timeline for that cosmic execution might be the most disturbing number of all. So, let's slow down for a moment right at the edge of that big rip forecast and take stock of how we got here. Because none of this comes from one wild data point or one dramatic press release. It comes from a pattern that keeps repeating across very different ways of looking at the universe. First, the expansion rate. JWST has joined a long line of space telescopes measuring how fast galaxies are racing away using type Ia supernovae, bright standard candle stars, and razor-sharp images of distant galaxies. The result? A Hubble constant on the high side again, lining up with local measurements and deepening the clash with early universe values from the cosmic microwave background. Prediction versus observation, and once more, the simple LCDM model strains. Then, JWST looked farther back in space and time than any previous mission. It discovered massive, well-formed galaxies just a few 100 million years after the Big Bang. In the standard picture, there just shouldn't be enough time for that much structure to grow. The cosmic web in JWST deep fields looks both too mature and, in some analyses, evolving in ways that suggest gravity, dark matter, and dark energy are not playing exactly the roles scientists assigned them. Add in those detailed gravitational lensing maps. Light from background galaxies is being bent into arcs and rings, letting JWST weigh invisible mass and trace how clumps of matter grow with time. Some of those measurements hint that structure growth is slightly suppressed compared to expectations, as if the cosmic expansion has been pushing outward a little harder than a true cosmological constant would allow. So the toolkit comes back into focus. A pure cosmological constant, WR1, should give a very specific expansion history and a very specific pattern of structure formation. Quintessence with W just above 1 and changing slowly would tilt that history, changing how quickly galaxies and clusters emerge. Phantom energy, with W below 1, would push harder, stretching space faster and faster, and leaving a sharper imprint on both distances and the clumpiness of matter. Tonight, we're going to treat these not as abstract symbols but as three competing scripts for the entire cosmic story. No one expects a single JWST field to settle the argument. No one predicts one supernova to overthrow Einstein. And absolutely no one anticipates that early galaxy counts alone will rewrite the laws of physics. Yet the whisper is there. High, H0. Early heavy galaxies, subtle shifts in lensing and structure growth. Each clue is deniable on its own. Together, they nudge the same way toward the unsettling possibility that dark energy is not a quiet, eternal constant, but a dynamic, possibly unstable field. By the end of tonight, you're going to understand why that distinction matters. Because if dark energy can change, it can grow. And if it keeps growing, the universe's ending won't be a gentle fade into darkness, but something far more abrupt. Now, let's begin the countdown to those doomsday scenarios and ask, what does each cosmic script actually do to galaxies, stars, and planets like ours? So before we race ahead into violent endings, pause on the version of the future that used to feel almost comforting. In the standard picture, dark energy is steady, unchanging, a quiet term in Einstein's equations with W=1. This is the LCDM universe, cosmological constant, cold dark matter, and a destiny that, while bleak, is not explosive. In that cosmos, expansion accelerates, but in a controlled way. Space stretches faster and faster, yet not fast enough to tear bound systems apart. Your local group of galaxies remains gravitationally bound, even as the wider web of galaxies drifts beyond reach. Trillions of years from now, the Milky Way, Andromeda, and their companions merge into one giant island galaxy, while everything beyond its shores slips across the observable boundary and fades from view. Tonight, we're going to sit with that long, slow fade. Star formation runs on a finite fuel supply. Gas clouds collapse into stars, stars fuse hydrogen into heavier elements, and radiation pours into space. But every burst of starlight is a withdrawal from a limited account. Over trillions of years, the cold reservoirs of gas are used up, locked into stars, planets, and dead remnants. New stars form more rarely. Then they stop forming at all. What remains is a universe of leftovers, white dwarfs slowly cooling into black dwarfs, neutron stars spinning down in the dark, black holes prowling the centers of galaxies, swallowing the last infalling gas, and stars. The bright, structured cosmos of the present gives way to a dim, skeletal system of degenerate objects and faint background radiation. The timescales are almost beyond imagination. Star formation dwindles over tens to hundreds of trillions of years. Gravitational encounters gradually eject stars from galaxies or send them spiraling into black holes over quadrillions of years. Then, on timescales around 10–100 years, even those black holes are expected to evaporate through Hawking radiation, bleeding their mass away into a trickle of low-energy photons. By the end of tonight, you're going to understand why that slow fade was once the good ending. In this heat-death scenario, dark energy never turns on us. It acts like a fixed background field, stretching space but not escalating without limit. No one predicts galaxies being shredded or planets ripped from their orbits. Instead, the universe drifts toward thermodynamic equilibrium, maximum entropy, minimum drama. The final state is a thin soup of particles and photons spread nearly uniformly across an ever-expanding space. No new structure forms, no new complexity arises. The cosmic mission is over, the instruments are still there, but the signal has faded into noise. Before we get started on the darker alternatives, hold that contrast in mind. This is the quiet, almost peaceful death scientists expected. No one expects the vacuum itself to become dangerous. Absolutely no one anticipates that dark energy might grow, turning this gentle twilight into a countdown towards something far more catastrophic. That quiet fade out is one possible ending, but it is not the only script the universe could follow. Change the sign or the strength of dark energy, and the same space that drifts into a gentle twilight could rush toward a catastrophic finale. Now, let's begin with the most dramatic alternative that dominated early thinking. The Big Crunch. Imagine that the total density of the universe, all the matter, dark matter, radiation, and any dark energy, is high enough that gravity wins. In that case, expansion does not go on forever. It slows. It stalls. Then, one day, it reverses. Every galaxy that is now racing away would begin to fall back, like a tossed ball reaching its peak and plunging down. In a true Big Crunch scenario, the scale of space shrinks. First, galaxy clusters collide more often, then galaxies merge in a cosmic traffic jam. Over unimaginable timescales, the entire observable universe collapses back in on itself, temperatures rise, densities soar, and the clock rewinds toward conditions as extreme as the Big Bang. If dark energy were absent or even negative, acting like an extra pull instead of a push, this fate becomes much easier to trigger. Before we get started on exotic modern models, it helps to see how seriously earlier scientists took this. In the early 20th century, once expansion was discovered, oscillating universes were a live option. Some cosmologists pictured a cosmos that cycles Big Bang, expansion, slowdown, contraction, Big Crunch, then perhaps another Big Bang. One universe after another, like a heartbeat on a cosmic scale. It sounds speculative now, but back then, with limited data, it was a respectable way to avoid a one-off creation event. Then came precision measurements. Type Ia supernovae, distant galaxies, and the cosmic microwave background all pointed the same way. Expansion is not slowing down, it is accelerating. The boundary where gravity should have started to win never appeared. That discovery, and now JWST's follow-up of supernovae and ancient galaxies at redshifts greater than 1, largely rules out a future crunch for our observable universe under simple models. Still, theorists are not done. There are big bounce ideas where a crunch triggers a rebound. Cyclic models where dark energy or modified gravity rhythmically stretch and squeeze space. Scenarios where the effective strength of gravity changes sign at extreme densities. These require new physics, beyond Einstein, and they remain highly speculative. But they show how sensitive the cosmic endgame is to whatever is driving acceleration. By the end of tonight, you're going to understand why current observations, including JWST's deep fields and lensing maps, overwhelmingly favor continued expansion. No Big Crunch on the schedule. Yet there is a catch. If dark energy evolves with time, if its pressure changes, if its equation of state slips below the cosmological constant value, the future can flip from endless expansion to violent transformation. No one expects the vacuum to change its mind. No one predicts that the same force now pushing galaxies apart could one day tear the very fabric of reality. But if JWST's hints of tension in our expansion history are real, the next scenario is far more unsettling than any crunch. A big rip, where the mission does not end with collapse, but with everything being pulled apart. This is the cosmic endgame almost absolutely no one anticipates. Not a gentle fade into darkness, not a dramatic collapse back into a fireball, but a universe that literally tears itself apart, layer by layer, as its own expansion runs out of control. Now, let's begin. To understand the Big Rip, there has to be a new player on the stage, phantom energy. In cosmology, dark energy is described by an equation of state parameter, W, which relates its pressure to its energy density. For a true cosmological constant, W equals 1, and the energy density stays the same as space expands. Phantom energy is what happens if W drops below 1. Then something deeply unintuitive occurs. As the universe gets bigger, the energy density doesn't thin out, it actually increases. That single inequality, W-1, changes everything. When space doubles in volume, instead of the same dark energy spread more thinly, more phantom energy appears. The expansion of space creates energy, and that extra energy drives even faster expansion. Faster expansion creates even more energy. It is a runaway feedback loop written directly into the fabric of space-time, and in the mathematics of the Friedmann equations, it ends with the scale factor blowing up to infinity in a finite amount of cosmic time. Tonight, we're going to follow that runaway all the way to its conclusion. In a phantom energy universe, the expansion rate keeps climbing until it starts to win against every known binding force. First, gravity inside galaxy clusters loses the tug-of-war, and clusters are pulled apart. Then, entire galaxies are unbound, their stars drifting away as the space between them stretches faster than their mutual gravity can respond. Later, even star systems are dismantled, planets torn from orbits as the cosmic expansion overwhelms the pull of their suns. Keep going. As the critical moment approaches, tidal forces from the accelerating expansion grow so extreme that planets, then stars, then even individual atoms can no longer hold together. Electrons are ripped from nuclei. Finally, nuclei themselves are shredded. The same smooth, dark energy that once seemed like a quiet background to the solar system becomes a universal demolition field. By the end of tonight, you're going to understand why the timeline for this apocalypse depends delicately on how far below one that W really is. If it is just a hair less than one, the Big Rip might be tens of billions of years away, long after every star in the Milky Way has exhausted its fuel. Push W further down, and the schedule tightens. Billions of years, then hundreds of millions, still far beyond human missions, but uncomfortably close on cosmic scales. Here is where JWST steps onto the boundary between theory and fate. By measuring distances and redshifts for galaxies and supernovae deep in space, scientists can reconstruct how the expansion rate has changed over time and pin down W with unprecedented precision. If, after years of observations, JWST data were to confirm W1 with high confidence, the Big Rip would no longer be a speculative branch on a cosmic flowchart. It would become a serious, data-driven candidate for how this universe ends. And the tension between what early universe physics predicts and what late universe spacecraft actually see would turn into a countdown. Before we get started on that countdown, there is one more, even stranger possibility, that W is not just less than one, but changing. If W is drifting downward, if dark energy is quietly slipping into the phantom zone, then the universe doesn't just fade, it comes apart, not in a blaze, but in a slow, accelerating unmaking that feels almost surgical. Now, let's begin. Picture the very distant future, trillions of years from now, when dark energy's strange pressure has intensified. Galaxies that are not gravitationally bound to our local group recede faster and faster. Their light stretches, reddens, and finally redshifts beyond our cosmic event horizon. One by one, island universes wink out. From our perspective, space doesn't feel crowded. It feels emptied. At first, local gravity wins. The Milky Way and Andromeda have long since merged. Our galaxy cluster orbits its own center of mass, apparently secure. Scientists once assumed that no cosmic expansion could pry apart a tightly bound system. But in a true phantom energy Big Rip, that expectation fails. The expansion rate itself accelerates so violently that the very definition of bound changes with time. As the critical time approaches, perhaps tens of millions of years before the final moment, the expansion on cluster scales grows comparable to the internal gravity that holds clusters together. Orbits no longer close. The great web of galaxies inside the cluster begins to unravel. First, the outskirts shear away. Then, over millions of years compressed by the runaway clock, even the core can't hold. The cluster dissolves into isolated galaxies carried apart by an ever faster cosmic wind. Closer in, the same pattern repeats. In the last few tens of thousands of years before the rip, individual galaxies lose their grip. Spiral arms stretch. Dark matter halos that once anchored stars are no longer strong enough to resist the metric expansion of space itself. The Milky Way remnant thins, then fragments. Stars that orbited peacefully for billions of years are flung onto trajectories that no longer loop back. By the end of tonight, you're going to understand just how personal this can get. In the final few months, the expansion rate on the scale of a solar system overtakes stellar gravity. Planetary orbits don't slowly widen, they fail. Worlds drift away from their stars as if the central mass had been dialed down to almost nothing. Tidal forces from the stretching of space outcompete the pull of the sun. Moons abandon planets. Asteroid belts smear into linear streams. Then the scale shrinks again. In the last minutes, the expansion becomes so extreme that it overwhelms electromagnetic forces. The bonds holding solid matter together snap. Mountains, oceans, spacecraft, even your own body would be torn into individual molecules, then into atoms. Seconds before the end, atoms themselves are ripped apart. Electrons are peeled from nuclei. Finally, even the strong nuclear force loses. Protons and neutrons shred into their constituent quarks. No one expects a cosmic apocalypse to look like this. No one predicts a fireball. Absolutely no one anticipates a single point of collapse. Instead, every point in space rushes away from every other point so fast that the very idea of distance stops making sense. There is no center, no edge, just a universal tearing. And if JWST is really seeing hints that W is sliding toward that regime, the next question is brutal. How long do we actually have before the countdown reaches zero? The countdown sounds terrifying. A universe that ends not with a whimper, but with a tear. But how close is that final second really to anything you would ever experience? Before we get started on the drama of the Big Rip, anchor this. Even in the most extreme phantom models that still fit current data, the doomsday clock is glacial, tens of billions of years, not millions, not the age of the solar system, far beyond the 5 billion year future when the sun swells into a red giant and sterilizes the inner planets. So, if the Big Rip is coming, humanity is not on the guest list. Our star will die, our solar system will be reshaped, and any trace of this civilization will be gone long before dark energy reaches its wildest phase. That contrast is important. The physics is violent. The timescale is almost incomprehensibly gentle on human terms. But what would the universe look like on the way there? Imagine going outside on a perfectly clear night. Right now, the Milky Way is a bright river across the sky, and telescopes reveal thousands of galaxies beyond. In a phantom energy future, that richness slowly drains away. As expansion accelerates, more and more distant galaxies cross a critical boundary, slipping beyond our cosmic horizon. No one expects a sudden jump. There is no visible wall. Galaxies do not blink out in a single evening over billions of years. Their light just never reaches us. The sky quietly empties. Long before any stars, planets, or atoms feel tidal tearing, observers in our local group would live in a cosmic island, surrounded only by the merged remnant of the Milky Way, Andromeda, and a few dwarf companions. Here's the pattern interrupt. On human timescales, nothing. No extra tug on the solar system, no slow stretching of your body. The change in the expansion rate across 1,000 years is so tiny that even the most precise planetary ranging experiments would not notice it. Across 1,000,000 years, it is still a subtle drift, buried under local gravity, stellar evolution, and the chaotic dance of planets. By the end of tonight, you're going to understand that the Big Rip, if real, is not a near-term threat. It is a thought experiment written into the deep future of space, a way to probe what dark energy actually is. The real urgency is not survival, it is opportunity. Tonight, we're going to use that urgency in a different way, because right now, in this brief window when galaxies are still visible and the cosmic wind of expansion is still gentle, JWST and other observatories can map how that wind changes with time. No one predicts these data will give simple answers. But the next step in the mission is clear. Measure the expansion with brutal precision and let the universe tell us which ending it has chosen. Measure the expansion with brutal precision, and something unexpected happens. The gentle cosmic wind looks calm on the surface, but in the equations there's room for it to turn into a hurricane. Tonight, we're going to follow one of the strangest possibilities, that dark energy could quietly change character and someday stop nudging the universe apart and start tearing it to pieces. In the simplest picture, dark energy is just a constant, Einstein's cosmological term with an equation of state parameter W locked at 1 forever. But many scientists have explored a more flexible idea called quintessence. Instead of a rigid constant, dark energy becomes a field pervading space, slowly rolling down an energy landscape. Early on, that roll can be so slow that W hovers very close to 1, perfectly mimicking a cosmological constant, while still having the freedom to drift as the mission of the universe unfolds. Change the shape of that landscape and the future changes with it. In some models, the field gradually loses energy and W creeps above 1, making dark energy weaken over time. In more exotic versions, interactions with other components of the cosmic system, like dark matter, can tug on the field, bend its trajectory, and even push W below 1. That threshold, W-1, is known as the phantom divide. Crossing it is not just a numerical game. On one side, the expansion accelerates but stays relatively controlled. On the other, energy density can grow with time, driving a runaway expansion that, in principle, could end in a big rip where galaxies, stars, and eventually atoms are torn apart by space itself. No one expects that transition to be easy to engineer in a consistent theory. Many simple phantom models come with serious problems: negative kinetic energy, instabilities where tiny quantum fluctuations blow up, or violations of cherished energy conditions in general relativity. Trying to glide smoothly across W-1 with a single well-behaved field tends to produce mathematical pathologies rather than a clean cosmic forecast. So theorists get more creative, multi-field constructions, where one field dominates early and another takes over later, can dodge some of those issues. Coupled dark energy models let the dark sector talk to itself, with energy flowing between dark matter and dark energy, letting W evolve from above 1 to below 1 over billions of years. By the end of tonight, you're going to understand why these models live or die on precision measurements. This is where JWST steps in, by tracking standard candles like type-Y supernovae and lensed galaxies far beyond what Hubble could see. JWST pins down how fast space was stretching at different cosmic times. If W has been drifting, even slightly, that drift leaves fingerprints in the way distant galaxies recede and how large-scale structure grows. So far, the data say W is very close to 1, but the error bars still leave a narrow corridor for evolution. The open question is brutal and simple. Are we catching dark energy in a calm, nearly constant phase, with more dramatic behavior still to come? Or is the universe already telling us that W is pinned at 1 and the big rip is off the table? Before we get started on the possible endings, JWST has one more surprise to add to the puzzle. JWST's surprise is this. When its deep fields and supernova follow-ups are folded into the cosmic expansion history, the best fit line for dark energy nudges below W1. Not by much, but enough that some scientists whisper a dangerous phrase, phantom energy. Now, let's begin. In normal dark energy models with W at 1 or slightly above, the underlying field behaves like a conventional form of energy. Its kinetic energy is positive. It fluctuates, it redshifts, it plays by the same broad quantum rules as the particles in every spacecraft and detector ever launched. Phantom models flip that script. To get W1, many of them invoke a field where the kinetic term comes in with the wrong sign, negative kinetic energy, a ghost. Negative kinetic energy sounds abstract, but the consequences are brutally concrete. In quantum field theory, the vacuum is never truly empty. It seethes with pairs of particles that pop in and out of existence. Give one of those fields negative kinetic energy, and the vacuum turns into a casino with a broken rulebook. Particle pairs can be created where one partner has positive energy and the ghost has negative energy, and the total still sums to 0. There is no upper limit. No one predicts when it stops, because it never does. That means unlimited particle production from nothing. The more pairs you create, the more the energy cancels, so the process doesn't cost the universe anything. The theory loses predictability. Calculations diverge. The vacuum itself becomes unstable on arbitrarily short timescales. For a mission to understand the real cosmos, that is a red flag the size of a solar system. To rescue W1 without detonating physics, theorists have tried to get clever. Some build modified gravity models where what looks like phantom behavior is really a trick of geometry, with extra curvature terms or extra dimensions changing how expansion responds to energy. Others add higher derivative terms so that the field can mimic negative pressure while keeping its true kinetic energy positive in a deeper description. There are effective field theories that allow phantom-like behavior, but only up to a certain energy scale, beyond which a more complete theory is supposed to restore sanity. Tonight, we're going to treat those as warning labels. By the end of tonight, you're going to understand why many cosmologists hesitate to take W1 at face value. When JWST hints at phantom territory, it might not be telling us that ghost fields truly fill space. It might be signaling that the current model of gravity or of dark energy as a smooth fluid is missing a crucial piece. That's what raises the stakes. A tiny deviation in W is not just a wiggle on a plot. It forces a choice. Embrace theories that threaten runaway instabilities, or admit that the foundations of the cosmic expansion model need to be rebuilt. And as JWST sharpens its measurements, the next data release could push that line decisively toward stability or toward a universe racing toward a fate far stranger than a simple Big Rip. So before the universe gets ripped apart by some runaway cosmic fuel, there's a radical escape hatch on the table. Maybe the problem isn't a mysterious dark energy at all. Maybe it's gravity itself that's misbehaving on the largest scales in space. Einstein's general relativity has ruled physics for more than a century. It predicts how planets orbit, how spacecraft slingshot through the solar system, how black holes bend light. Every local test, from Mercury's orbit to gravitational waves, lines up with eerie precision. But those tests live in a tiny corner of reality. They probe solar and galactic neighborhoods, not the full cosmic web stretching billions of light years beyond. Tonight, we're going to step back and ask a forbidden question. What if general relativity is only an approximation, and the rules of gravity slowly drift as you zoom out to the scale of galaxy clusters and beyond? In that picture, the apparent push of dark energy is not a new ingredient in the universe. It's the symptom of using the wrong gravitational law at the largest boundary of our observations. That's where modified gravity models come in. In far gravity, the simple curvature term in Einstein's equations is replaced by a more flexible function, letting space itself respond differently in low-density regions. In DGP brainworld models, our universe is a 4D membrane floating in a higher dimensional bulk, so gravity can leak into extra dimensions at huge distances, weakening or reshaping the cosmic pull. Massive gravity goes even further and gives the graviton, the carrier of the gravitational interaction, a tiny mass, changing how attraction works over intergalactic scales. On paper, these theories can mimic accelerated expansion without a cosmological constant. The expansion history can look almost identical to LCDM, but the growth of structure and the way light bends do not. That's the key. By the end of tonight, you're going to understand why JWST is suddenly one of the most powerful gravity detectors in existence, even though it never measures gravity directly. JWST's ultra-sharp images let scientists map gravitational lensing in exquisite detail, tracing how galaxy clusters warp the paths of photons from even more distant galaxies. At the same time, its deep surveys track how matter clumps over time, how fast tiny ripples in the early universe grew into the vast filaments and voids of today. Compare those two maps, how matter clusters and how light curves, and you get a brutal test of the underlying gravitational law. Pattern interrupt. If dark energy were just a smooth background fluid, you would expect one specific relationship between clustering and lensing. Change gravity instead, and that relationship shifts. The expansion may look the same, but the cosmic scaffolding does not. So far, general relativity has passed every local exam with flying colours, but on true cosmological scales, the tests are still crude. JWST sharpens them, turning fuzzy hints into precise constraints. If JWST-era data keeps straining LCDM, the community faces a stark choice: embrace a weird, evolving dark energy that could tear the universe apart, or accept that gravity itself is far stranger than Einstein ever imagined. And the next round of observations will start to corner that choice. If dark energy is evolving, it does more than tweak a few parameters. It rewrites the schedule of the entire cosmos. The universe still expands, still cools, still forms galaxies and planets, and eventually, you. But the order and timing of those events shift in ways that leave fingerprints all across space. In the standard LCDM picture, the early universe is ruled by matter. Gravity wins, pulling gas into growing clumps, while dark energy sits in the background, almost irrelevant. Only a few billion years in does the balance tip. the expansion starts to accelerate and dark energy takes over. That tipping point has a redshift, a specific when in cosmic history. If dark energy's density changes with time, that redshift moves. Acceleration might have started earlier or later than scientists currently calculate. Expectation meets reality in a very direct way here. Change when acceleration begins, and the growth of structure changes with it. If dark energy was weaker in the distant past, gravity had a longer, cleaner window to operate. Clumps of matter could grow faster, halos could collapse earlier, massive galaxies could assemble surprisingly quickly. Suddenly, those JWST images of bright, heavy galaxies less than 500 million years after the Big Bang do not look like outlaws. They look like the natural outcome of a universe where the cosmic brake pedal of dark energy was not yet fully pressed. Tonight, we're going to lean into that idea because evolving dark energy also distorts the way distances map onto redshifts. Astronomers do not measure expansion by watching galaxies move in real time. They infer it from how bright things appear and how stretched their light becomes. Change W as a function of redshift, WZ, and the distance redshift relation bends. Type Ia supernovae at a given redshift might appear slightly brighter or dimmer. The apparent angular size of the baryon acoustic oscillation scale, this frozen ripple from the early universe, shifts on the sky. By the end of tonight, you're going to understand why that is so dangerous and so powerful. The same evolving WZ that can help with early massive galaxies must also pass a gauntlet of precision tests. It alters the integrated Sachs-Wolf effect, the tiny boost in cosmic microwave background photons as they climb out of decaying gravitational wells in an accelerating universe. It nudges lensing patterns, late-time temperature anisotropies, and cross-correlations between the CMB and galaxy surveys. No one predicts a free lunch here. Any evolving dark energy model has to thread a needle between early universe and late universe constraints. JWST's galaxies, supernovae, and lensing arcs cannot be read in isolation. They must plug into a single, self-consistent cosmic timeline. The choice is stark. Either LCDM bends a little to accommodate a flexible, time-varying dark energy, or the mission is about to reveal that something even deeper, gravity itself, needs to be rebuilt from the ground up. Now, let's begin. How close are scientists to proving that dark energy really changes with time, instead of sitting there like a silent cosmological constant? The honest answer is uncomfortable. The numbers are whispering. They are not yet shouting. Combine the best measurements of the expansion of space so far, type Ia supernovae, galaxy clustering, weak lensing, the cosmic microwave background, and a pattern emerges. The equation of state parameter W, which tells you how dark energy pushes on the fabric of the universe, still comes out very close to 1. Within the error bars, a true cosmological constant still fits. There are hints, small tilts in the probability curves, that W might dip below 1 or drift with redshift. But those hints depend on which data sets are combined, which models are assumed, and how flexible the fitting functions for WZ are allowed to be. Prediction versus observation is the entire game. And before declaring that prediction has finally lost, that dark energy is evolving, every hidden source of error has to be hunted down. That is where systematic uncertainties become the real enemy. Calibration errors in how bright a supernova truly is, selection biases that favor galaxies that are easier to detect, or lensing systems that look cleaner, modeling assumptions about dust, about star formation histories. about how mass is distributed in a lensing galaxy or cluster. Each one can gently tilt the inferred value of W without any new physics at all. No one expects the universe to confess easily. To claim evolving dark energy with a straight face, those systematics have to be beaten below the level of the signal. That means independent teams, independent instruments, and independent methods all converging on the same answer. Tonight, we're going to see why JWST is only the first wave of that assault. Its deep fields and time domain programs will track supernovae and lensed galaxies at redshifts that Hubble could barely touch, extending direct expansion measurements far deeper into cosmic time. But it will not act alone. Euclid is mapping billions of galaxies to chart the large-scale structure of the solar neighborhood of the universe and beyond. The Roman Space Telescope will turn the sky into a precision dark energy survey machine. DESI is already measuring tens of millions of galaxy and quasar redshifts from the ground, tracing the imprint of acoustic waves frozen into the cosmic web. By the end of tonight, you're going to understand why one probe is never enough. A robust detection of evolving dark energy demands that the expansion history, the growth of structure, and the pattern of gravitational lensing all point to the same WZ curve. The boundary between interesting tension and new physics is crossed only when supernovae, galaxies, clusters, and lensing arcs all tell the same, impossible-to-ignore story. Right now, the field is at an inflection point. JWST has raised the stakes, sharpened the questions, and exposed cracks in the old, smooth picture. But the final verdict on dark energy's constancy is still being written. And if the next round of missions push W below one in unison, the universe's future will look far more violent than anyone predicts. So, before the universe can be torn apart, there's a quieter question to settle. What exactly is doing the tearing? Now, let's begin. When cosmologists say dark energy, it sounds like a new kind of substance, some exotic fuel-filling space that scientists might someday bottle up in a lab. That picture is wrong. Dark energy, as used in modern physics, is first and foremost a term in the equations, a way of saying that on the largest scales, space-time itself behaves as if it's imbued with a very specific kind of energy. In Einstein's general relativity, mass is only half the story. Energy and pressure also tell space-time how to curve. Normal matter, radiation, even the solar wind all have positive pressure or behave like they want gravity to pull things together, slowing expansion. Dark energy is different. It acts like a component with negative pressure. That negative pressure shows up in the equations as a repulsive effect. Instead of expansion decelerating under gravity, it accelerates. This isn't a new force in the same sense as electromagnetism. There is no dark energy particle pushing on galaxies the way photons push on a solar sail. In the standard picture, galaxies are mostly at rest in the expanding fabric of space. As that fabric stretches, the distance between galaxy clusters grows. Dark energy is the rule book for how fast that stretching speeds up. But what is it made of? That's where the mystery deepens. It could be vacuum energy, the energy of empty space predicted by quantum fields. It could be a new scalar field, gently rolling over cosmic time. It could be an emergent property of space-time, something that only appears when the universe is viewed as a whole, or it could be telling us that general relativity itself breaks down in the ultra-large, low-curvature, so-called infrared regime. No one expects a single telescope to answer that, yet JWST is forcing the question. Pattern interrupt. Dark energy is not dark matter's cousin. They share a name and nothing else. Dark matter clumps? forms halos, anchors galaxies and planets through gravity. Dark energy does not clump. It is smooth, almost perfectly uniform, and it dominates only on scales where galaxy clusters look like mere points. It also is not a cosmic wind shoving the Milky Way through space. The motion of our solar system through the galaxy and the galaxy through the larger cosmic web is governed by gravity from matter, not by dark energy blowing past like air. By the end of tonight, you're going to understand one more crucial point. Locally, dark energy is almost irrelevant. It does not noticeably affect planetary orbits, spacecraft trajectories, or the solar system's internal dynamics. On those scales, its influence is drowned out by ordinary gravity. But stretch your view to the edge of the observable universe, to the boundary where light has barely had time to reach us, and dark energy takes center stage. It shapes what edge even means, and it decides which regions of space remain forever beyond reach. Tonight, we're going to follow that edge and see how dark energy is quietly redrawing it. So where does a universe like that actually end? Not at a wall of galaxies, not at a shell of frozen planets, but at a set of invisible horizons that only make sense when space itself is accelerating. Before we get started, forget the idea of a single edge. In an expanding universe, there are several different boundaries, and each one answers a different question. The particle horizon tells you how far light has traveled since the Big Bang, defining the largest region that has ever been in causal contact with us. The Hubble radius marks the distance where galaxies recede at the speed of light, given the current expansion rate. And then there is the strangest one of all, the cosmic event horizon. The particle horizon is about history. The Hubble radius is about the expansion right now. But the event horizon is about the future. It is the ultimate limit on what events can ever influence an observer, even if that observer waits forever. In a universe dominated by dark energy, this event horizon is not just large, it is permanent. Tonight, we're going to stand at that horizon. In the standard LCDM picture, dark energy behaves like a true cosmological constant. The expansion of space accelerates, but in a controlled, predictable way. As this acceleration takes over, the event horizon settles down to a fixed physical distance, on the order of tens of billions of light years. Everything inside that radius remains, in principle, part of one connected system. Everything beyond it is exiled forever. This sounds abstract, but it is as real as the heliopause is to a spacecraft. Galaxies that cross that cosmic boundary are not moving through space faster than light. Instead, the space between you and them is stretching so quickly that their future light can never catch up. No matter how long the mission lasts, no signal, no solar wind, no photon from those regions will ever reach you. By the end of tonight, you're going to understand why JWST's dark energy hints are really horizon hints. If dark energy is not constant, if it slowly evolves, or if it belongs to a class of models called phantom energy, the event horizon does not stay put, it moves. In phantom scenarios, the energy density of the vacuum increases over time. Expansion does not just accelerate, it runs away. The event horizon shrinks, slicing more and more of the universe off from any given observer. First, distant galaxy clusters disappear beyond the boundary, then neighboring galaxies. Then, in a true big rip, even the gravitationally bound solar system, even planets, even atoms are torn apart as the horizon collapses inward. No one predicts that outcome with confidence yet. But JWST's measurements of how fast distant galaxies recede and how early structure formed are the first precise tests of whether our cosmic horizon will remain stable, or whether the very definition of reachable universe is slowly tightening toward a final tier. Now, let's begin. So when that horizon tightens, when the reachable universe shrinks on paper, it sounds abstract. But you have seen this pattern before on a much smaller scale. To understand what James Webb is doing to the edge of the universe, you go back to the missions that redefined the edge of the solar system. Before we get started, remember how simple the picture used to be. There was the sun, the planets, and then, somewhere out there, a clean line where the solar wind stopped and interstellar space began. One boundary, one frontier. That's what most scientists drew on diagrams. Reality did not cooperate. Voyager 1 and 2 flew outward expecting a neat cutoff. Designed for a 5-year mission to study the giant planets, the spacecraft ended up dissecting a layered, shifting frontier that absolutely no one anticipates in full. First came the termination shock, where the solar wind, racing out at hundreds of kilometers per second, suddenly slowed below supersonic speeds. Then, farther than every model predicted, they crossed the heliopause, the contact surface where the solar system's magnetic bubble gives way to the galactic medium. Beyond that, there might be a bow shock or bow wave where our entire system plows through the interstellar wind. One edge turned into 3 different transitions, each with its own physics, each at a different distance, each challenging the old solar system map. Tonight, we're going to use that as a template for the universe itself, because the cosmos does not have a simple rim either. It has an observable boundary, set by the finite speed of light and the age of the universe. It has a causal boundary, beyond which events can never influence you no matter how long you wait. And it has horizons sculpted by dark energy, where space expands so fast that even light can never cross back. By the end of tonight, you're going to understand that these cosmic edges are not fixed lines drawn on a static background. They are moving targets defined by expansion, gravity, and the changing pressure of dark energy, just as the heliosphere's boundary swells and contracts with the solar wind. And just as Voyager discovered the heliopause was farther, stranger, and more asymmetric than every textbook claimed, JWST is now finding that the universe's own boundaries don't quite match the neat, theoretical curves. Galaxies appear too massive, too early. The rate at which distant space stretches does not perfectly agree with the rate inferred from the early universe. The clean division between nearby and cosmological distances blurs when dark energy's influence is written into the equations. There is a human pattern here. Draw a simple border around the known system. Send a better spacecraft. Watch the border fracture into layers, flows, and hidden dangers. The edge is always more subtle, more dynamic, and sometimes more threatening than expected. So if Voyager turned the solar system's edge into a complex, living structure, what is James Webb about to do to the universe's edge? And what does that mean for a cosmos that might one day tear itself apart? Tonight, we're going to pull apart the hype from the hard data. Because when it comes to dark energy, James Webb has already changed the conversation, but not always in the way headlines claim. Now, let's begin. The first thing Webb has confirmed is that cosmic acceleration is real, and it's not going away. By tracking distant galaxies' lensed arcs and follow-up Type Ia supernovae, scientists can measure how fast space itself is stretching at different times in cosmic history. Those late-time measurements still come out higher than the rate predicted from the early universe locked into the cosmic microwave background. The Hubble tension survives. In fact, with Webb's precision, that disagreement looks sharper, not softer. Expectation. A single, clean expansion story from Big Bang to now. Reality. Early universe data and late universe data refuse to agree on the tempo of the cosmic expansion. That alone doesn't prove dark energy is evolving, but it corners the standard model and asks hard questions about what's really driving the acceleration. Then Webb did something unexpected. It looked back to just a few 100 million years after the Big Bang and discovered fully formed, massive galaxies that should have taken much longer to assemble under the simplest LCDM timelines. Huge stellar masses, surprisingly ordered disks, and rich structure appear earlier than many simulations predicted. No one expects that level of maturity in a universe that young. No one predicts that the first generation of galaxies would look this grown up. There are two broad options. Either galaxy formation is more efficient and violent than the models captured, new feedback, faster star formation, denser dark matter halos, or the underlying cosmology, including how dark energy and gravity behave, needs subtle tuning. Not a total rewrite of Einstein, but a quiet adjustment in how structure grows in an accelerating space. Here is the key boundary. JWST observations so far are consistent with dark energy having an equation of state, very close to a cosmological constant, W1. The data do not demand exotic physics, but they also do not lock the door. Mild evolution in W with time is still allowed, slowly rolling quintessence fields, or even slightly phantom-like behavior where W dips below 1 remain on the table. Pattern interrupt. This does not mean James Webb has proven a big rip. There is no direct measurement saying the solar system, the planets, or atoms will be torn apart on a fixed date. What Webb has done is more subtle and more unsettling. By deepening the Hubble tension and revealing early structures that strain the simplest growth histories, it has made evolving dark energy impossible to dismiss as fringe speculation. Models that once lived at the edges of conferences are now debated in the mainstream. By the end of tonight, you're going to understand that Webb's real confirmation is this: the picture of a perfectly simple, perfectly constant, dark energy was too naive. The universe's long-term fate is not settled, and the next observations could push that fate toward gentle heat death, or something far more dramatic. So what does it actually mean to live in a universe whose long-term fate just slipped out of our grasp again? For most of human history, questions like that didn't belong to laboratories or telescopes. They belonged to myth, to philosophy, to stories told under dark skies about how the world began and how it would end. Back then, the cosmos was a dome or an egg or a celestial clockwork pushed by gods. There were no redshifts, no standard candles, no spacecraft in orbit around distant planets. The mission was survival on Earth, not measuring the expansion of space. Now, in a single human lifetime, scientists have gone from arguing about the age of the solar system to timing the universe's heartbeat with supernovae and the afterglow of the Big Bang. That's the strange position you are in. Tonight, we're going to talk about a species that can chart the universe's past in exquisite detail, project its possible futures with differential equations, and yet has to admit, about 70% of the cosmic energy budget is an unknown component with unknown long-term behavior. The expansion can be measured, the models can be run. But the thing driving that expansion? Its true nature still hides beyond the current boundary of understanding. It's a contrast that would have sounded impossible even a century ago. On one side, precision, Galaxies whose light has traveled more than 13 billion years, mapped by JWST. Supernovae whose brightness lets spacecraft and ground telescopes trace how the cosmic wind of expansion has changed over time. On the other side, mystery. Dark energy that might stay calm, slowly thinning into heat death, or that might grow, tilting the universe toward a big rip where even atoms are torn apart. Psychologically, that hits differently for different people. Some hear Big Rip and picture every galaxy, every star, every solar system shredded by runaway expansion, and feel a very real chill. Others look at the timescales, tens of billions, maybe trillions of years, and it becomes abstract, like worrying about the weather on a planet in another galaxy. And for many, the dominant feeling is awe. Awe that a primate brain on a wet rock around a very average star can even glimpse these endgames. Before we get started on judging that uncertainty as comforting or terrifying, it helps to remember what science actually does. Uncertainty is not a failure mode. It is the engine. No one expects JWST to hand over a final answer engraved on a golden plate. No one predicts a single graph where dark energy's value is fixed forever. What Webb does is sharper. It takes old certainties, stresses them, and replaces them with better questions and tighter tests. So, if the universe's fate is now less settled than many textbooks promised, that does not push you outside the mission of this channel. It puts you right at the center of it. The goal here has never been to offer a perfectly safe, perfectly closed picture of space. It has been to invite you into the real frontier, where models break, data argues back, and curiosity wins over comfort. By the end of tonight, you're going to understand that living with cosmic uncertainty is not a flaw in how you think. It is a feature of being a conscious part of a changing universe. The next step is to see what happens when that uncertainty collides with something even more unsettling. The possibility that our measurements of expansion don't agree with each other at all. That disagreement is not going to fade on its own. It will be hammered, mapped, and cross-examined by a new generation of instruments that, together, will turn the entire sky into a laboratory for dark energy. Now, let's begin with the big picture. JWST is a narrow, piercing spotlight drilling deep into the early universe. The next decade belongs to wide eyes. Missions like Euclid, the Nancy Grace Roman Space Telescope, DESI on the ground, and the Rubin Observatory's LSST will not stare at one tiny patch of space. They will sweep the whole sky again and again, building a dynamic atlas of billions of galaxies. The contrast is deliberate. JWST shows how galaxies looked when the universe was a few 100 million years old. Euclid and Roman will show how those galaxies and their descendants arrange themselves across hundreds of millions of light years. Their cameras are designed for weak lensing, the tiny, systematic distortions in galaxy shapes caused by foreground mass. From those distortions, scientists reconstruct the invisible scaffolding of dark matter and the way it grows under the pull and the push of dark energy. At the same time, DESI is already collecting spectra for tens of millions of galaxies and quasars, while LSST will track their positions and brightness changes over a decade. Together, they will trace baryon acoustic oscillations, subtle ripples in the large-scale pattern of galaxies, fossil echoes of sound waves in the early plasma of the young solar system's parent galaxy. The size of those ripples is known. How that standard ruler appears stretched or compressed at different distances locks down the expansion history and tightens constraints on W, the dark energy equation of state parameter, and how it might evolve with time. This is where the synergy becomes dangerous for complacent theories. JWST gives an exquisitely detailed high redshift snapshot of structure just coming online. Euclid, Roman, Deci, and LSST fill in the middle and late universe from cosmic noon to the present day. Stitch them together, and you do not just get isolated frames. You get a time-lapse of how clumps form, merge, and thin out as space itself accelerates. If dark energy has ever changed its strength, that continuous movie of structure growth is where the fingerprints will show up. And then there are the standard sirens as gravitational wave detectors upgrade. LIGO, Virgo, Cagra, and future missions like LISA, they will hear more neutron star mergers across cosmic time. Each merger is a self-calibrating distance marker. Combine that distance with a redshift from ordinary telescopes, and the expansion rate falls out with no dependence on traditional candles. It is a completely different way to measure the same cosmic wind. Tonight, we're going to live in a rare moment. Within 1 or 2 decades, either all of these independent probes will converge on a truly constant dark energy, or they will refuse to agree. If W stays pinned at 1, the big rip retreats back into speculation. If it drifts, even slightly, the idea that space could one day tear galaxies, stars, and atoms apart moves from nightmare scenario to testable forecast. No one expects the universe to give up that answer quietly. The real shock comes if these telescopes discover that the problem is not just dark energy at all, that the underlying law of gravity itself may be starting to crack. So now you need a new picture in your head. Not the tidy, textbook universe that glides along on a simple equation, but a restless cosmos where even the rulebook might be under negotiation. Before we get started on that mental reset, rewind the mission. In the late 1990s, distant supernovae revealed that cosmic expansion is speeding up, not slowing down. No one expects that. Scientists patch the equations with a cosmological constant folded into a model called LCDM, and for a while it works beautifully. The universe looks like a clean system. Dark matter shapes galaxies, dark energy is a smooth background push, and gravity plays by Einstein's rules. Then, JWST launches and the whole mission changes. Tonight, we're going to think of Webb not just as a telescope, but as a time machine and a stress test. It stares into deep fields, measures redshifts out past Z-10, watches type Ia supernovae fade in galaxies that formed when the universe was a fraction of its current age, and traces gravitational lensing arcs that reveal where invisible mass hides. Each of those measurements is another ruler laid across the expanding fabric of space. By the end of tonight, you're going to understand why those rulers no longer line up. The Hubble tension is real, and Webb sharpens it. Early universe readings from the cosmic microwave background point to 1 expansion rate. Late universe readings from supernovae and standard candles point to a faster one. JWST pushes those late measurements deeper into time, and the disagreement does not dissolve. It hardens. At the same time, the early structure of the universe looks too grown up. Massive, well-formed galaxies appear just a few 100 million years after the Big Bang. The boundary between primordial chaos and settled cosmic web is closer than models predicted. Either dark matter clumps more efficiently, gravity behaves differently on large scales, or dark energy's influence has not been as steady as LCDM assumes. Here is your new mental model. Imagine the universe as a woven fabric. Galaxies, clusters, and filaments are the knots and patterns in the weave. Dark matter is the hidden thread holding those patterns together. Dark energy is the invisible hand stretching the cloth. LCDM said that hand pulls with a constant, uniform force. JWST has turned on the lights and revealed subtle warps. The early knots are tighter than expected. The spacing between them changes in ways that hint the pull may have varied over time. Now, let's begin to place the future on that fabric. If the pull stays nearly constant, expansion keeps accelerating but gently. Galaxies drift apart, stars burn out, and heat death wins. If dark energy weakens or flips sign, the fabric could sag and collapse in a big crunch. If it strengthens with time, phantom energy, its grip tightens and the fabric doesn't just stretch, it tears. Galaxies unbind, stars shred, atoms rip. No one predicts that outcome with confidence yet. But absolutely no one anticipates the universe to be as simple as the old model promised. The key transformation is this. You no longer see dark energy as a quiet, background number. You see it as a live parameter in a cosmic experiment, one that JWST is now running in real time. And that experiment is not just about how the universe expands. It is about whether the very law of gravity, the force that built planets, stars, and the solar system itself can survive the pressures of deep time without breaking. So now, the question hanging over all of this is simple and brutal. What does it mean that a metal and gold eye in space is putting gravity itself on trial across the whole universe? Think about the arc of this mission. Engineers set out to build a telescope cold enough to read the faint heat from the first galaxies to catch photons that have been stretching through space since before the solar system existed. Designed to map a cosmic dawn, and now that same observatory is being used to glimpse possible cosmic midnight, testing whether dark energy will lull the universe into a quiet fade or drive it toward a final tearing wind. The contrast is almost absurd. A fragile observatory a few meters across, with mirrors thinner than a human fingernail, floating in the dark beyond the moon, shielded from the sun by a folded plastic kite. Against that, a universe 93 billion light-years wide, filled with planets, stars, and galaxies, all of them caught in an expansion that may never stop. A single spacecraft, balanced at a gravitational boundary, quietly measuring the fate of everything. No one expects a machine so small to reach so far into deep time. No one predicts that tiny shifts in the colors of distant galaxies could hint at how the entire cosmic story ends. Yet this is exactly what scientists have discovered JWST can do: turn the sky into a laboratory, and the last 13 billion years into a controlled experiment on dark energy. And it is not the work of one genius or one late-night idea. It is thousands of people across decades, mirror polishers and cryo-engineers, flight controllers and data analysts, the teams planning supernova follow-ups and gravitational lensing surveys, all of them orbiting a single question: what kind of universe do we live in? A universe where expansion coasts, a universe where it accelerates, or a universe where, in the far future, space itself might rip galaxies, stars, and even atoms apart. Here is the part that often goes unsaid. By the end of tonight, you're going to understand that you are woven into that same mission. By choosing to spend nearly 2 hours thinking about dark energy and cosmic destiny, you are doing the same thing those scientists are doing, pushing against the boundary of ignorance, refusing to let the universe remain a backdrop you never examine. Tonight, we're going to take that curiosity and carry it forward. Black holes that rewrite what gravity can do. Inflation that may connect our universe to something beyond. The next wave of JWST surprises that absolutely no one anticipates. Now, let's begin the next chapter of this journey together. Tonight, we're going to leave with something most people never get from a video about dark energy. A map. Not a perfect one, not a final one, but a clear sense of where the mystery stands, and where this mission through the dark is heading next. By the end of tonight, you're going to understand how far that map already reaches. You've seen what dark energy is in the simplest terms, a pressure in space itself that drives the expansion of the universe faster and faster. You've seen the Hubble tension, early universe measurements from the cosmic microwave background pointing to one expansion rate, late universe standard candles pointing to another, and JWST stepping in with sharper eyes that deepen, not erase, the disagreement. You've watched scientists use this spacecraft to track distant supernovae, gravitationally lensed galaxies and ancient structures more than 13 billion light-years away, turning the sky into a laboratory for cosmic acceleration. You've followed how those measurements hint that dark energy might not be constant and how a changing equation of state could lead, in the far future, to galaxies torn from clusters, stars torn from galaxies, and in the most extreme Big Rip scenarios, atoms torn from themselves. If that picture feels terrifying and beautiful at the same time, that reaction is exactly right. It means you're not just hearing about space as trivia, you're seeing the solar system and the cosmos as a living experiment still in progress. No one expects the universe to explain itself. Scientists have to drag those explanations out of the data. One redshift, one spectrum, one strange galaxy at a time. So, here is the ask. If you see yourself as the kind of person who wants to follow this story as new observations arrive, who wants to be there the night a mission like JWST, Euclid, or the Nancy Grace Roman Space Telescope finally shows whether dark energy is steady, drifting, or racing towards something catastrophic, then subscribe. Join the group that refuses to look away from the boundary where theory and observation clash. Likes and comments are more than fuel for an algorithm. They are a way to steer this channel toward the questions that keep you awake. Leave a comment if you want deep dives into modified gravity, into quantum vacuum energy, and the zero-point fields that might underlie dark energy, into the physics of cosmic horizons, and what it really means for regions of space to slip forever beyond causal contact. Coming up, there's a full narrative on the Hubble tension itself, prediction versus observation, early versus late universe, and what happens if the numbers never reconcile. There's an exploration of how Euclid and Roman will join JWST in mapping the dark universe, charting the cosmic web, and measuring the solar wind of expansion that pushes every galaxy away from every other. The universe may be racing toward an end no one predicts, and absolutely no one anticipates. But together, watching every new photon these spacecraft return, we can at least make sure we see it coming. And the real twist is that the next signal from the dark might already be on its way.